Are you curious about how your computer manages its memory and input-output operations? This video explores the techniques used by modern operating systems to handle these crucial tasks. Discover the methods that keep your system running smoothly and efficiently. Logical address space is an abstraction that allows programs to think they have more memory than physically available. This virtual view simplifies programming by decoupling program memory from actual hardware constraints, enabling features like multitasking and memory protection. Physical address space refers to the actual RAM. It is the real hardware memory available in the system where programs and data must ultimately reside for execution. Dynamic relocation helps map logical to physical addresses. This is typically handled by the Memory Management Unit, MMU, which uses base and limit registers or page tables to translate addresses during runtime. This mapping ensures efficient memory use by allowing flexible allocation and protecting processes from interfering with each other's memory spaces. Understanding these concepts is vital for managing memory effectively, as they form the foundation for implementing paging, segmentation, and virtual memory key techniques in modern operating systems. Memory can be allocated in contiguous blocks or through paging. Contiguous allocation can lead to fragmentation. Paging divides memory into fixed-size blocks, reducing fragmentation. Different fitting strategies optimize memory use. These strategies ensure processes get the memory they need. Static loading involves loading all program components at once. This means that all instructions, libraries, and modules are brought into memory before execution begins, which can simplify program execution and reduce runtime overhead. Static loading can waste memory if components are unused. When unused functions or libraries are loaded regardless of need, they occupy valuable memory space, leading to inefficiencies, especially in resource-constrained environments. Dynamic loading loads components as needed. In this approach, modules are loaded into memory only when they are called during execution, often using system calls like DLOP and DAO in Unix-based systems. Dynamic loading is more efficient for large applications. It reduces initial memory footprint and enables better scalability and modular design, allowing updates or patches without recompiling the entire program. Both methods have their advantages and challenges. While static loading offers simplicity and potentially faster execution start, dynamic loading offers flexibility and efficiency at the cost of increased runtime complexity and potential loading delays. Swapping moves in active processes to disk to free up RAM. Virtual memory uses disk space to extend RAM capacity. These techniques allow large programs to run smoothly. They ensure that active processes have the memory they need. Efficient swapping and virtual memory use are key to system performance. Device drivers enable communication between the OS and hardware. They translate OS commands into hardware actions. Drivers ensure devices function correctly. They play a crucial role in system stability and performance. Understanding drivers is essential for managing hardware efficiently. There are user mode, kernel, and virtual drivers. These represent different levels at which drivers interact with the operating system and hardware. User mode drivers run in user space and are safer. Since they are isolated from the core operating system, crashes or bugs in user mode drivers are less likely to affect system stability. They are commonly used for less performance-critical devices such as printers or USB peripherals. Kernel drivers operate in the OS kernel and offer high performance. They have direct access to system resources, allowing fast and efficient communication with hardware. However, any fault in a kernel driver can lead to system crashes or security vulnerabilities, making stability and security testing essential. Virtual drivers simulate hardware. They are used when no physical device exists, such as in virtual machines or when creating emulated environments. These drivers allow guest systems to interact with virtual hardware for testing, development, or sandboxing purposes. Each type has specific use cases and benefits. The choice depends on the balance between performance, security, complexity, and the nature of the hardware or virtual environment involved. File systems manage how data is stored and retrieved. Common types include FAT32, NTFS, and ext4. Each file system has unique features and limitations. Understanding these systems is crucial for data management. They impact performance and compatibility. Journaling helps recover data after crashes. It keeps a log, or journal, of changes before they are actually committed to the file system, enabling the system to replay or discard incomplete operations after an unexpected shutdown, thus preventing data corruption. File permissions enhance security. They control who can read, write, or execute files by assigning access rights to users and groups. This helps prevent unauthorized access. Accidental deletion or malicious tampering of critical files. These features are vital for data integrity. They work together to ensure that data remains accurate, consistent, and protected from corruption or misuse. Even under failure conditions or in multi-user environments, choosing the right file system is important for system reliability. Different file systems such as NTFS, ext4, or APFS offer varying levels of performance. Journaling, encryption, and compatibility. Selecting one that aligns with system requirements and usage patterns enhances overall stability and resilience. File systems handle reading, writing, and managing files. Caching speeds up file access by storing data temporarily. Efficient caching improves system performance. It's crucial for handling large files and frequent access. Understanding caching strategies is essential for optimizing file operations. Different file systems offer various performance levels. FAT32 is simple and widely compatible. NTFS provides robust security and large file support. exFAT combines compatibility with large file handling. Choosing the right system depends on your needs. Memory management ensures efficient use of resources. Approaches include single contiguous allocation and partitioning. Paging and segmentation offer more flexibility. Virtual memory extends RAM using disk space. Each method has unique benefits and challenges. This method allocates all memory to a single process. Known as single contiguous allocation, it dedicates the entire available memory space to one program during execution. It's simple but inefficient for multitasking. Since only one process can reside in memory at a time, multiple programs cannot run concurrently, making it unsuitable for modern multitasking environments. Memory can be wasted if not fully used. If the allocated process doesn't utilize the entire memory block, the remaining space stays idle, leading to internal fragmentation and inefficient memory utilization. It's best for simple systems with one task. Embedded systems or very early computing environments, where multitasking isn't required, may still use this method due to its straightforward implementation. Understanding its limitations is key for efficient memory use. Recognizing when this approach becomes a bottleneck helps in transitioning to more advanced techniques like partitioned memory or paging, which offer better flexibility and resource management. Fixed partitioning divides memory into set sizes. Dynamic partitioning adjusts sizes as needed. Fixed partitioning can lead to wasted space. Dynamic partitioning reduces waste but can cause fragmentation. Each method suits different system needs. Paging divides memory into fixed-size blocks. It eliminates external fragmentation. Pages are mapped to available frames. This method supports non-contiguous allocation. Paging is essential for modern operating systems. Segmentation divides memory into logical units. Each segment reflects a program's structure. It allows for modular and protected memory use. However, it can lead to external fragmentation. Segmentation is useful for structured programs. Virtual memory uses disk space to extend RAM. It allows larger programs to run smoothly. The OS swaps inactive processes to disk. This frees up RAM for active tasks. Virtual memory is crucial for modern multitasking systems. Drivers translate OS commands into hardware actions. They ensure compatibility and functionality. Drivers manage data flow between OS and devices. They handle interrupts and control commands. Efficient drivers are key for system stability. Virtual memory is slower than RAM. Excessive swapping can degrade performance. It's best as a backup when RAM is full, not a substitute for actual memory. Understanding its limits is important for system efficiency. Paging eliminates external fragmentation. It supports larger than RAM programs. However, it requires managing page tables. Page table lookups can slow access. Despite its challenges, paging is vital for modern OS. Fixed loading loads all components at start. This means that the entire program, including all modules and dependencies, is loaded into memory before execution begins. It ensures all resources are immediately available but may increase startup time and memory usage. Dynamic loading loads as needed. Program components such as libraries or modules are loaded into memory only when they are required during execution. This can reduce the initial memory footprint and allows for greater flexibility and modularity. Fixed linking includes libraries in the executable. All required code from external libraries is copied directly into the final binary at compile time, resulting in a larger executable but eliminating external dependencies during runtime. Dynamic linking links libraries at runtime. Instead of embedding them into the executable, the program relies on shared libraries, .dll or .so files, that are loaded when the application runs. This allows updates or bug fixes in shared libraries without recompiling the program. Both methods have unique advantages and challenges. Fixed methods offer stability and independence from external files, while dynamic methods promote flexibility, efficient memory use, and ease of maintenance, though they may introduce dependency management and version control issues. In conclusion, efficient memory and I/O management are crucial for system performance. They directly influence how quickly and reliably applications run, as well as how effectively hardware resources are utilized. Modern operating systems use advanced techniques to ensure smooth operation. These include virtual memory, caching, buffering, DMA, direct memory access, and interrupt-driven I/O, each designed to maximize efficiency, responsiveness, and stability. Understanding these methods helps optimize computer use. Whether you're a developer, IT professional, or everyday user, a solid grasp of memory and I/O processes enables smarter troubleshooting, system configuration, and performance tuning. From memory allocation to device drivers, each component plays a vital role. They work together to create a seamless interaction between software and hardware, ensuring that user tasks are carried out reliably and efficiently. With this knowledge, you can enhance your computing experience. Being aware of how the underlying systems function allows you to efficient memory and I/O management are crucial for system performance. Modern operating systems use advanced techniques to ensure smooth operation. Understanding these methods helps optimize computer use. From memory allocation to device drivers, each component plays a vital role. With this knowledge, you can enhance your computing experience. Thank you.